Hello everyone. So we have Bob Kleinberg from Kleinberg today. He would be talking about unconventional fossil fuels, and he's been working with Kleinberg for almost like 3.5 decades. So he has been in the industry for a while, and you can feel free to ask any question related to the subject. He has absolutely expertise in this. I mean, 3.5 decades is a lot. Okay, I'll let him take a time.
Okay, thank you. It is always a pleasure to be here at Harvard. And this is actually the fourth time I've given this lecture for ES231, so you'd think it would be a pretty dull, worked over subject by now, but actually every year it's different, partially because the field of unconventional fossil fuels is advancing so rapidly, and partly because I sort of purposely put in new topics, and there's always so many things to lecture. I've sort of been asking Mike if he would just give me a whole course, but that hasn't happened yet. Anyway, this is an outline of what we're going to be talking about today. I pledged to finish by 4 o'clock. I was a student once too, and I remember very well the agony of running 3 minutes overtime. So first part is going to be about reserves and resources. These words are frequently confused, sometimes even within the industry. And you, as informed citizens, should understand the difference. And also, I'm going to be talking about conventional versus unconventional fossil fuels. What's the difference, and sort of give you a quick overview. Most of the lecture today will be about the two most important unconventional fossil fuels, which are gas shale and tight oil. You've probably read about them in the newspaper. It has everything to do with fracking, which I'm sure you've heard about, and horizontal drilling. That's going to be the focus. There's a lot of other topics, as you'll see, but unfortunately they're going to be neglected in the interests of at least covering those two with some depth. So with that focus in mind, we're going to be talking about petroleum geology, which sounds pretty dry, but actually I think it's one of the most entertaining parts of this lecture. Then sort of the technical heart, which is the permeability problem, and well construction technology. I think you'll find that kind of interesting. And then just some quick words on the economic and environmental consequences and sort of the unintended consequences of some of these developments. So diving into it, first talking about reserves and resources. Mike actually asked me to put this up because I think he himself was a little bit confused, but basically, this is the sort of diagram that is now accepted in the oil and gas industry and by the Securities and Exchange Commission to classify reserves and resources. And sort of the big subdivisions, so the overall box is, the size of the box is determined by total petroleum initially in place. And there's a box for oil and there's a box for gas. They look the same, but oil and gas are not both present in here. This is one or the other. And the major subdivisions are discovered petroleum in place and undiscovered petroleum in place. And within those two large subdivisions, there are 6 boxes. The one at the top is the oil or gas that has already been produced. We know exactly how much that is. In the case of oil, it's 1.2 trillion barrels, which is a sphere about 4.5 kilometers in diameter. Kind of a sickening thought, but an awful lot of oil. So that's what's already been produced. The next box in the green are reserves, and that's what's economically recoverable. The proved reserves are what gets reported to the Securities and Exchange Commission, and that's the part of the reserves that has a 90% probability of recovery. Now, basically, these reserves are economically recoverable. In other words, it makes economic sense to extract them at today's price. And interestingly, last year, the gas reserves of the United States went down because the price of gas went down. So everybody had to recalculate their reserves according to the lower price of gas, and some of the gas that they had booked was no longer economic because it would cost too much to produce, more than the market price. That's kind of an interesting little sideline. Now, going this way, because this is geology and nothing is ever really known, about geology in terms of the size of the reservoirs and the amount of oil in a given rock body and so on. There's only probabilistic determinations of how much oil or gas you might have. And so basically, if you have a 90% probability that you're pretty sure you know what you've got, it's in this box, a 50% probability of being able to produce this stuff is this much, and a 10% probability of being able to produce all that. So that's what the horizontal axis means. Now, the next box down are now we get into the resources as opposed to reserves, and these are technically recoverable using today's technology. So not necessarily economic, but technical. And those are things we can get out if we don't worry about the price. And again, there's a 10%, 50%, and 90% probability of recovery in that also. The fourth of these boxes, is the not technically recoverable but discovered resource. So you found some stuff, but you have no idea how to get it out. That's what goes, and believe me, this will come up later as an important factor. That's what goes in this box. Then we have the undiscovered petroleum, and you think, excuse me, what's that doing there? If it's undiscovered, how do we know it's there? But the U.S. Geological Survey has made sort of a cottage industry of estimating how much oil or gas there might be in sort of geological basins that have not yet been drilled. If it's not drilled, you don't really know what you've got, but using analogies and sort of geological smarts and so on, they come up with these estimates for the undiscovered oil in place. And generally, they're actually pretty credible estimates, and they're taken seriously. That is divided into the technically recoverable, undiscovered, and the unrecoverable, undiscovered. If you're unrecoverable and undiscovered, you've got a problem. But that's the dullest part of the talk, so let's get past that. But now you know these terms, and it is important to understand them and you'll see from now on, when you read newspaper articles and so on, you'll see how often these are misused. Okay, what are unconventional resources? Unconventional resources are fossil fuels for which production technology is not yet mature or environmental issues are not yet resolved. And that's basically what we're going to be talking about today. By production technology not yet mature, what I mean is, yes, we have a way of getting this stuff out of the ground, but we know it is far from optimized. So that's really the situation we have today, this tight oil and gas shale resource. The environmental issues also are subject to a process of maturation. Generally, early in the game, you make a lot of big mistakes, like gushers and so on. As time goes on, hopefully things get better. So I put that as a criterion for unconventional. So I just put this into your packet. I'm not going to go through this. It is way too big and too many boxes. But just to give you an overview of the liquid fuels picture, this is published by the International Energy Agency in Paris. Every year they put out a World Energy Outlook, a big book, which is worth reading if you're in the field. So liquids, of course, there's biofuels down here, and then there's oil up here. Conventional oil is sort of the light tan boxes, and then the unconventional oil are these sort of brown boxes. And you'll see that there's really a lot of different kinds of unconventional oil. There's extra heavy oil, light tight oil, which is what we're going to be talking about today, gas to liquids, coal to liquids. And I believe Professor Aziz has discussed some of these in other lectures, certainly in his book that he's working on. So I'm not going to, the only one I'm going to talk about is this box here. But that's, again, for your reference in your packet. So let's just look at some numbers. So as I said, the total amount of oil that has been produced in all of human history is about 1.2 trillion barrels. That's that 4.5 kilometer sphere. Now, the International Energy Agency estimates that about that much again will be used by 2035, roughly 20 years away now. So our use is accelerating. Our booked reserves are about 1.6 trillion barrels. So that's what's on the books with the Securities and Exchange Commission and similar agencies in other countries. It's always embarrassing when these things pop up, isn't it? Okay, we're not going to worry about that. And then these resources, sort of the technically recoverable, is basically this light tan box of conventional oil. So basically, this is the conventional oil line, 3 trillion barrels. The USGS estimated that a long time ago, and the number is held up pretty well. So they're doing a good job. Now, the red here is this light tight oil. This is what comes out of these so-called shale resources, which are going to be the subject today. And as you see, back in 2012, way back in 2012, the IEA was estimating, well, we've got that much, so many 100 billion barrels. A year later, our Energy Information Administration, a US government agency that does a lot of energy statistics, sort of had increased that by 50%. So this box is growing as we speak, and getting bigger and bigger. Then we got the extra heavy oil, Karajan oil, and so on. So the total remaining resource is 6 trillion barrels. Some argue that much of that will never be produced because of global warming, climate change concerns. That could well be true. We certainly have a lot of petroleum in the ground. We've got, one might even say, more than enough. So we're not just going to run out of oil and gas. So this is a scorecard. Again, I'm not going to go through every box, but I've sort of listed the most important unconventional oils and the most and the most common unconventional sources of gas. Again, we're going to be looking in the red boxes here, but I think you can pretty well guess what the coding is. Green means good, like green in the size column means we got a lot of it. Cost, green means low cost, red means high cost. Technology means we pretty much know how to produce it, or things are sort of well along the way. Commercialization, green is basically totally commercialized, sort of in the product stream. Yellow is sort of, there's some use of it here and there. Red, not yet commercial. Environmental issues, I think you can also guess the meaning of that. Red's bad, green's good. I've assigned this sort of yellow and green because we're doing better with tight oil environmental issues, but I'd say we're not there yet. Political risk, green is good, obviously. The heavy oil is sort of coated with red and green because half of it comes from Venezuela, half from Canada. So Venezuela is kind of red and Canada is good. So anyway, again, you could sort of muse on this at your leisure, which I'm sure is abundant. Let's move to the petroleum geology part. Now we're going to see where these things come from. So this is really basic. Basically, the story is that hydrocarbon fuels come from organic matter that has settled to the bottom of shallow anoxic lakes, inland seas, marine environments, and so on, been buried by various geological processes, which we're going to talk about in a minute, buried to depth. The earth gets hotter as you go down, so it's exposed. So what I call the compressed dead algae is getting hotter and hotter, and then is converted to oil and gas. And that's what happens in this purple band, which is called source rock. Now, when the compressed dead algae is converted to oil and gas, the oil and gas is less dense than the water that's around it and everything else that's around it. So it tends to want to migrate up in the earth, and frequently will find some migration path, which could be a fault, or it could be a fault that's actually produced by the pressure of the nascent hydrocarbons. So that is also a frequent path. And it will migrate upwards. Sometimes it will get to the surface, disappear into the biosphere, where it's oxidized, goes away, and we never see it again. But sometimes it encounters what is called seal rock, which is this gray, same color as seals. I'm a San Franciscan, so I know what they look like. Where we have seal rock, actually. And basically, the oil and gas that's migrating upwards gets trapped under there, and beneath the seal rock or cap rock, there's what's called reservoir rock. And it is rock that is fairly porous and permeable to fluids. Now, what do I mean by porous? Sedimentary rock, and think of beach sand, think of sand dunes in a desert, think of coral reefs. When you take that and sort of pack it together tightly, there's still a fair bit of empty space. And a good sedimentary rock, even with the grains cemented together, could have as much as 30% empty space in between the 70% of solid mineral matter, which is quartz or carbonate mineral or whatever. So 30% of the rock mass is available to take fluids, and the gas, which is red here, coated red, floats on top of oil, that floats on top of water, occupying that pore space. And that's what's called an oil or gas reservoir, and that's where we've been producing oil and gas from for the last 150 years, very successfully. Again, the two things that are important about this rock: porous, 20 or 30%, think about those numbers, and permeable, which means fluid flows relatively easily through it. You can think of these rocks like sponges, where water is relatively easily flowing through, or oil or gas. And so these systems are buoyancy-driven systems, and that's a very, very important concept, and you'll see why a little bit later. Okay, that's what we've been exploiting for 150 years. So where's this unconventional, where's this shale stuff that we have to frack? That's down back in the source rock. That is oil and gas that has been generated but never left. No path out. And it's just been stuck there. It is not separated by buoyancy. It's all mixed up together. And generally, the porosity is much lower, maybe 5% instead of 30%. And as you'll see in a minute, the permeability to fluid flow is very, very low. If it were high, it would have escaped. So that is the basics of petroleum geology in one slide. Okay, so let's just look at a few more details about this maturation process. Again, we start with organic matter that's been buried. And these are some very typical numbers. So this is distance into the Earth in kilometers, so 7 kilometers here. And there's a sort of global average geothermal gradient of about 30 degrees C per kilometer. It varies from place to place. Volcanic regions, it's going to be much higher, et cetera, et cetera. But that's kind of a good global average, good number to focus on. Surface temperature, 25 degrees centigrade, more or less global average. And so these are the temperatures associated with the depths. Now, the organic matter, which is long hydrocarbon molecules, okay, like biochemicals, at high temperature start cleaving into smaller molecules like octane, pentane, and so on, which are sort of gasoline components or crude oil components. And that happens at a relatively low temperature. That starts happening around 70 degrees centigrade. Now, if you took some sludge or whatever, your favorite organic material in your kitchen, and kept it at 70 degrees centigrade for a year, not much would happen. The reason is that basically the chemical reaction proceeds according to the Arrhenius equation, and generally there's a summation of those exponential terms that accurately describe the transformation called pyrolysis. But basically, if you want to produce oil at 70 degrees C, you really need to have a few million years. It takes millions of years. However, if you are impatient, let's say that you want to produce oil in a few weeks in your kitchen, then you're talking about 350 degrees centigrade. Not ridiculous. I mean, it's hotter than your kitchen oven, but we do it in the lab all the time. If you want to produce oil in an hour, 500 degrees centigrade. That takes, and that's all the same kinetics as what occurs in the Earth, with the same coefficients even. This has been checked out, very thoroughly studied. Now this is getting annoying. But basically, these are the depths and temperatures corresponding to millions of years availability of time. And then at higher temperatures, then the biomolecules crack even more into smaller pieces, and that's wet gas. What is wet gas? Wet gas is methane plus ethane, propane, butane, pentane. Even hotter, dry gas. What is dry gas? Just methane. You know, when you start breaking up the pentane to methane, then you're really down in this hot region, which is about 180 degrees and above. So actually, we're used to finding methane reservoirs at 180 degrees centigrade at very great depths, but that is not true of these shale gases, and you'll see why in a minute.
So artificially produced oil and like naturally produced oil, are they of the same quality? Like, do they have the same components?
No. That's a really good question. The 500-degree pyrolysis, 500-degree C pyrolysis, gives you a product that has a lot more sort of undesirable products, aromatics, and so on. The Earth does a really great job of producing high-quality, excellent hydrocarbon. But even if you're willing to wait a few days and do the 350 degrees C, you get a good middle distillate. I mean, actually, this is something I know a lot about, which is like a C15 oil, which is like kerosene, jet fuel. You can get a good jet fuel if you're willing to wait 4 days. That's not bad. Yeah.
And I'm wondering, in your talk about the temperature dependency of the different, like methane, pentane, different ratio, but where are those hydrogen or carbon goes? I mean, if you always produce dry gas, you need to input much more hydrogen or get away a lot of carbon, right? So where does this thing go?
Right. Very good. I didn't mention that.
Repeat the question for the mic.
Yes, right. Okay, the question was, as you break these biomolecules into smaller and smaller pieces, the ratio of hydrogen to carbon gets larger. So whereas the original biomolecule is like a CH2, the methane that you produce in the end is a CH4. Where'd that hydrogen come from? Well, no extra hydrogen came into the system, obviously. But carbon was rejected from it. So, and what you have left, going back to the sketch, what you have left here in this source rock is basically carbon. It's called pyrobitumen. And it's got almost no hydrogen left in it. So you reject it, it's left behind and sort of stored in the rock. And the importance of that you'll see in a minute. And so I'm very glad you asked that question. You'll find that that is a very key question as we go on. Okay. And by the way, you certainly are welcome to ask questions as we go. And I will not run over, no matter how many questions you ask. Okay, so now some places you find oil and some places you find gas. Why? Let's look at an example. This is in central Texas. Here's Dallas. Tarrant County, which is Fort Worth. In Tarrant County, generally if you drill there, you get mostly gas. But if you just go 100 miles to the west to Eastland County, you get mostly oil. Why is that? What's 100 miles? So let's just try and figure out why. So to understand why Tarrant County is different than Eastland County, you have to know what the Earth looked like back in the Mississippian 340 million years ago. And this is what it looked like. It was weirdly different than today, as you see. And anything that you think you recognize is a false cognate. So for example, North America wasn't in the northern hemisphere. It was actually an equatorial continent. This mountain range, which is one of the largest topographic features on Earth at the time, is the Appalachian Mountains, which somehow is running west to east instead of north to south. Strange. And then Africa is down here. kind of below where South America should be, I guess. But anyway, it was all very scrambled. And I think you all know about plate tectonics, so perhaps this is not a huge surprise to you. This is a closer look, and that Mississippian time period, 325 million years ago, I think this map is in particular. And this is the United States. I'm sorry, the outlines of the states are light, but I will point out sort of kind of the major ones. Let's see, we have New York State up here, Pennsylvania here. Again, here's the Appalachians parallel to the equator, which is running up here. So we're south of the equator. Fort Worth Basin, obviously in the middle of Texas, is here. The Deseret Basin is Utah, of course, and California, kind of these offshore islands. Now, what was going on was that Africa was sort of threateningly approaching us and creating these island arcs, which are somewhat analogous to the Philippines and Japan, which is what's happening in the West Pacific today, and as the plates are sort of being pushed together. And so you can see in these light blue areas, these are areas of shallow seas, equatorial, which are going to be very productive of organic matter, which is then going to die and go to the bottom. And so when you think about analogs today, you think, wow, Bengal, Sea of Bengal, Bay of Bengal, thank you. Bay of Bengal is one place. South China Sea is a great place to accumulate organic matter. That's where I'm going to go in 100 million years and get my oil. But clearly, Fort Worth was a great place back then. And so and Africa is sort of approaching, and then it's going to override the North American continent in this big collision, which formed Pangaea, continent which no longer exists. So here's the geological time scale at the top, and M is Mississippian, and the thin blue band is what's called the Barnett Shale. Now, this is a burial history diagram, and these are just packed with information. It's really fascinating. So the vertical axis is the depth below the surface, and the horizontal axis is the time in millions of years ago. So here's 500 million years ago up to the present at 0. And this goes down to 20,000 feet or 6 kilometers. So you can see in Eastland, Texas, the Barnett Shale, where all that organic matter was laid down in that shallow inland sea, was pushed down all the way down to 8,000 feet. And if you go through the little calculation with a 30 degrees C per kilometer and the 2.7 kilometers in the surface temperature, you get 100 degrees C, and that's the oil window. So hey, whoa, it produced oil just like it should have, and there it is. So that kind of explains it. Now, since then, this mountain range, which was created when the continents collided, it was called the Ouachita Mountains. Anyone ever hear of the Ouachita Mountains? No, neither had I. They don't exist any. Oh, one person maybe? Somebody from Oklahoma?
I do work in the Delaware.
Okay, yes, all right. So this is a mountain range that basically doesn't exist anymore. It was completely eroded. And in the process of erosion, the Barnett Shale moved from sort of 8,000 feet below the surface now to its present depth at about, what, 4,000 or something like that. So that Barnett Shale, that organic rich shale, which is producing oil, is now a lot shallower than you would otherwise expect it to be. Okay. Let's look at Tarrant County, the one that's more to the east that was producing gas. Same process, Pangaea, okay, there we go, about the same time. And however, it was pushed all the way down to about 14,000 feet and attained a temperature of about 150 degrees centigrade, which is in the gas window. So what's happening is that Tarrant County was closer to the point of collision than Eastland County, and therefore was pushed down much deeper. And that's why we get gas there. So it's really, you have to go back and see what's happened through geological time to understand how these things occurred. And now in the Fort Worth area, the Barnett Shale is now about 8,000 feet deep, and that's gas. And again, you would never expect to find gas at 8,000 feet if it hadn't been buried much more deeply at some point in the past, and then come up due to the erosion of this formerly huge mountain chain. So this is a map of the shale gas plays of North America. This red line is the suture where Africa collided with North America back there, hundreds of millions of years ago. And you can see that there's one big play after another. The Marcellus up here, Fayetteville, Woodford, Barnett, and so on. These are all famous names in the industry that are now prolific sources of oil and gas. Now, you'll also see that there's a lot of stuff going on in the western United States and western Canada. This is a different geological event, happened at a different time, hundreds of millions of years later. Similar story, with the sedimentary basins and the tectonics and so on. But it's a different story, but basically the same idea. And so, this is how you go around, and this is your first level of prospecting for oil and gas, for those of you who want to prospect for oil and gas.
What you just described, is that also true for Eagle Ford, that there's some gas and some oil?
Oh, Eagle Ford is a great example because it is graded. It's in bands. So on the Gulf Coast, it's very deep and you have gas. And then just going relatively small distances, you get into wet gas, volatile oils, black oils. It's like a geochemistry textbook. Yeah. So absolutely. Yeah. And that had to do with the formation of the Gulf of Mexico and so on. So that was a different geological story, but at a different time. But again, same principles apply. Okay, so back to this kind of boring reserve and resource chart that I showed you earlier. In the United States, there have been about 1 million wells drilled, 1 million oil and gas wells drilled. We are the most thoroughly drilled place in the universe. And so we've been drilling all these wells. The subsurface geology is very well defined. People have been doing geochemistry for years on source rocks. They used to be considered kind of cranks in the industry because why are you interested in source rock? All the oil and gas is in those reservoirs up above, but nonetheless, people do research. Those people are now superstars. But basically, these resources were well defined quite a long time ago. And they were considered discovered, but not technically recoverable because we didn't know how. We figured these rocks have such low porosity, such low permeability to fluids that we're never going to be able to get oil and gas out of them, so they are firmly in this category. Nonetheless, when we did figure out how to produce shale gas and tight oil, then they rapidly moved up to the top box and are now being considered reserves. So that's the US story, kind of in a resource story, kind of in a nutshell. The rest of the world is different. The rest of the world is not as much drilled. Now the basic geology is known and the tectonics, the big global, the globes of colliding continents, that's all known. But nonetheless, because the wells haven't been drilled, we don't have that geochemical knowledge of exactly how deep they got at various times, what's been produced, if anything. So really, the rest of the world, unconventional resources, is down here in what's really undiscovered. We have no idea how big this resource is, and people are slowly, trying to find out in places like Russia and China and Poland and so on. But we're on sort of on two speeds. There's the American race car, which is going around really fast, and then there's kind of the rest of the world jalopy, which is moving along more slowly. They will catch up, however. But that's kind of what's going on sort of in a geopolitical sense today. Okay, the permeability problem. So this is kind of the technical heart of the story. Now, I told you that reservoirs consisted of porous and permeable rock. Typically, it might be, think about a sand dune that's grains have been cemented together, or a beach, Grains have been cemented together. That's a typical reservoir. And then there's a cap rock up above, which is impermeable. And here, in this case, this particular reservoir, I forget which one it is, that cap rock comprises clay and calcite. But this is the reservoir. And basically, this is going to be, we know how to produce this. So this is old-fashioned conventional stuff. This is the new sorts of plays that we're dealing with now. And there's no cap rock. It's mineralogically sort of uniform over its entire section. And the pore space, which is encoded here in these sort of reddish colors, is clogged with kerogen. Now, kerogen, as I mentioned earlier, is basically that carbon that was left behind. And instead of the pore space being filled with water, oil, and gas, all of which are reasonably mobile, now it's filled with this solid carbon. This is a problem. Let's look at it in more detail. So on the left is a SEM micrograph of a really good conventional reservoir rock. And here are those sand grains I've been telling you about, nice big sand grains, 50 micron scale bar. And there's the pores. Wow. Now those pores are about the same diameter as a hair, human hair. I said this was a really great reservoir. It is remarkable that rock in which the pores are as fine as human hair is a really good reservoir. Oil and gas do flow relatively easily through such a thing. Look at this picture on the right. This whole red box corresponds to sort of the size of this red box over here. This did not come from here. This is just for scale purposes. And here's the scale bar. This is 50 microns. This is 500 nanometers, half a micron. So now it's 100x more magnification. And now the pore is filled with this sort of stuff. And this is basically the pyrobitumen, or the rejected carbon that was left behind, and plus some clay. And you can see that it itself is porous. Now, why is it porous? It's porous because when the oil and gas gets produced, it escapes, so you have less matter left behind. And so what you are left with is sort of a porous solid material that's carbonaceous. Now, those pores, however, are not those nice big 50 micron pores. They are 50 nanometer pores, 1,000 times smaller, 1,000 times smaller. This is not good. This is why people in the oil and gas industry considered this not technically recoverable, and I'll show you why. When you talk about the flow of fluids through porous media, it's governed by Darcy's law. Darcy's law is the same as Ohm's law. Basically, you have a driving term, which in the case of fluids is a pressure gradient. In the case of electrons, it's voltage, same thing. You have a current. This is a mass flow with dimensions of cubic centimeters of fluid per square centimeter per second. So that's the flux, and that corresponds to a current density. And then the conductivity term is this K over mu. Okay, what is K and mu? Mu is viscosity, okay? And K is this new term, which you're probably unfamiliar with, permeability. Permeability is basically the ability of a porous medium to transmit fluid. The dimensions of permeability are meters squared. The practical unit is a Darcy, which is 10 to the minus 12 meters squared. And it is proportional to the square of the pore size. So you can imagine that if you have a porous material, the smaller the pores, the harder it is for fluid to get through it. And that is absolutely definitely true according to the pore size squared. So looking at some and then here, just so Darcy is sort of a made-up unit, but here are consistent units that make the equation work dimensionally. So if you have a water filter, sort of home water filter, swimming pool water filter, that's good for about 10 Darcys. A really good oil reservoir like the one I showed you on the last slide, maybe 1/10 of a Darcy. Gas shale reservoir, 10 to the minus 7. Why is it 10 to the minus 7? Because I told you that These pores are 1,000 times smaller than these pores. 1,000 times squared, 10 to the 6th. Wow, not technically recoverable. Absolutely not. Now, if there's oil here and gas here, you do get 2 orders of magnitude back because you've got viscosity in the denominator, viscosity of crude oil, typically 1 centipoise, like water, that's your standard oil, and natural gas at reservoir conditions about 10 to the minus 2 centipoise. So you do get back a factor of 100 from the denominator, but you're still short a factor of 10 to the 4th. So this is looking pretty desperate because you cannot drill a well and expect fluids to come out 10,000 times slower and think that that's going to be economic under any circumstances. Forget it. Not going to happen. Now, the other part of this equation is how much of the rock is exposed to the borehole that you've drilled. How much? So basically, typical borehole, 8-inch diameter, 20 centimeters. Typical productive formation, 30 meters. More, I mean, they vary a lot, but certainly that would be considered reasonable average. So if you calculate the surface area of that cylinder, not too hard to do, you come up with about 20 square meters of exposure, and that's adequate if you have this kind of reservoir with the 10 to the minus 1 Darcy. That's adequate. But how are you going to overcome the 10 to the 4th deficit that you have in permeability? Fracking. That's the answer. And coupled with horizontal well construction. So looking at those numbers, if you drill a well instead of vertically where it only intersects 30 meters of productive formation, if you had some way, how could you possibly do this? But if you had some way of turning the drill bit in the productive formation and following it for a mile, and then fracturing it many, many, many times over its entire height, 30 meters, plus maybe out 100 meters because these geological layers are laterally extended a long way. 100 meters is certainly just a small part of that. And let's say that you have 30 of those fractures, then you can develop 100,000 square meters of reservoir contact, because now it's not just this perimeter, but it's this plus these fracture wings, which are going out in both directions. And that's how you can get, you know, when you go from 20 to 100,000, there's your 10 to the 4th. That's the secret. I put this in, again, more for reference than as part of the lecture, but I've just described the situation with shale gas, which has the low porosity and very, very small pore spaces. Tight oil, which is developed in exactly the same way with horizontal wells and hydraulic fracturing, has to have permeability that's substantially higher because you've got to overcome the factor of 100 in viscosity. Oil's 100 times more viscous than gas. So you find that this tight oil that's now produced with massive fracturing comes from reservoirs with higher permeability like this, and then the more conventional plays are shown here. Tight gas is sort of an intermediate case where you just fracture once, and that's been done for a long time. But this is, again, more for reference than to continue the argument. Okay, so now we know what we need to do. We need to increase the contact area of the borehole by a factor of 10 to the 4th. How to do it? So this is the cartoon. I'm sure you've seen these in newspapers and so on. This is probably, you know, the best publicized story in science over the last 5 years, I would say, science and technology. So the basic plan is that you drill from the surface down to the productive zone, somehow turn the drill bit, drill for about, so basically you're drilling down between 1.5 and 4 kilometers. Then your horizontal run is 1 to 3 kilometers, and then you fracture it along the way. You get 10 to 30 fractures. There may be diameter sort of bi-wing is maybe 600 meters, and that gives you the 10 to the 4th surface area enhancement that you need to make all this work. that's the overview. Now, what about this horizontal drilling? Actually, this turns out to be sort of easier than you might think. There's numerous clever devices to get the drill bit to turn, and the advantage is, of course, if you tried this with your home, Black & Decker, it's not going to work. But because these wells are kilometers deep, and you're drilling with 4-inch steel drill pipe, hollow pipe, and you can imagine putting a 4-inch pipe on maybe a pipe stand, and you can imagine it drooping. Well, we're going to take advantage of that flexibility of the steel to make sure that it can go around corners, and in fact, you can actually get that, you can push that steel so it'll bend about 10 degrees per 100 feet, interesting, and that's good enough for what you need to do. So now the only problem is you've got to be guiding the front part of the drill so it's doing the bending the right way. And this is one of several clever devices. This is actually not a Schlumberger device, it's somebody else's, but it's very illustrative. And basically, this is what's called a drill collar. You screw the drill bit onto this end, which is this big, ugly 8-inch thing that grinds rock up, you can imagine. The miles and miles of pipe get screwed onto that end, but this is sort of the intelligent part. And this thing has these 3 sort of flaps shown here in cross-section that are actuated by pistons. Now, there is some intelligence in this, so that let's say that you want to rotate from going vertical to horizontal out in this direction. Then whenever a pad finds itself at the low part of the rotation, the piston actuates, pushes out the pad, and that makes the drill bit sort of angle up a little bit. And then as this pipe rotates from the top, that's what the drilling rig, the thing that you see at the surface does, basically rotates pipe. This thing then gets rotated into the bottom position, and that gets pushed out. And then this thing gets rotated to the bottom position, that gets pushed. So it keeps getting nudged a little bit at a time into the direction you want it to go. And you can go not only from vertical to horizontal using this system, but you can turn to the left, turn to the right, go up, whatever you want. So it's very versatile. And there is sort of a lot of built-in intelligence. It's obviously got, I guess there's a compass in it, so it knows which way it's going. There's some tilt sensor, so it knows what the tilt is, and some sort of feedback mechanism. So you send a command down, turn right, and the thing knows the commands it needs to send to the pads to turn right. So it's pretty clever. And these things do work remarkably well. Now this is not Schlumberger, this is some brand X, but their assignment was to drill between the magenta and cyan bands, whatever they were. I have no idea why, but anyway, that was their assignment. And you can see they did a pretty good job. Now, this is the horizontal direction here is thousands of feet, so 8,000 to 16,000 feet. The vertical axis is very much exaggerated. Each box here is 25 feet, whereas each one of these boxes is 1,000 feet. So there's a lot of vertical exaggeration here to make a nice figure. But you can see that this being 25 feet, they were staying within, a foot, a couple of feet of their objective, so they were doing a pretty good job. Now here they got to a fault where the Earth had sort of, caused the rock layers to separate. They had sensors, they realized that, so they had to start steering, and within, less than 1,000 feet, say, they were sort of back on track and once again between, magenta and cyan. So, and like I said, this was brand X. Schlumberger could do even better. But, so this gives you an idea of how precisely these can be steered these days.
Question?
Yes.
Do you have to wait for the tailings to come back out to tell you that you left one area or another, or is there marks down the field?
Yeah, Fred, that is a great question. So there are a myriad of sensing means to tell you where you are, to do the navigation, if you will. So the most sophisticated is an electromagnetic device which is based on the electrical contrast between magenta and cyan. That's a very straightforward method. And so in general, each of these layers has a different electrical resistivity, and the azimuth of the drill bit is known from its internal sensors. So you know whether the higher resistivity is above you, you want to make sure it's above you, and you want to make sure it's 10 feet above you, or whatever. And that's one way to steer. There are many other methods, but that gives you an example of how that can be done. Yeah. So you have active sensing of where you are. Yeah, that's a very good question. Okay, now, Professor Aziz once asked me, well, how fast do these things rotate? It rotates at about 1 revolution per second. So the mechanics, the mechanisms of this are not super demanding from the standpoint of the rapidity of the response. However, it is a very harsh environment. You're talking about, up to 175 degrees centigrade, 20,000 psi, shock and vibration all over the place. I mean, hundreds of Gs, thousands of Gs maybe. So the equipment has to be pretty robust, but what you might call the smarts of it, or the computations to get the steering right are not too sophisticated. It's not real high speed. So if you can steer the drill bit, you can drill from anywhere to anywhere. That's actually kind of liberating. So this is an example. This is from a gas shale play in Texas, Arlington, Texas. And basically, this is the campus of the University of Texas at Arlington. And all the drilling occurred on this one 5-acre well site. And you can see they drilled 19 wells. Basically, the entire campus is on production for natural gas, plus this sort of what looks like maybe a light industrial area to the south, and even this kind of very nice residential area off to the east here. But basically, they were able to do all this drilling over miles. I mean, they were able to drain miles from this one 5-acre site. Now, for those of you who aren't farmers, 5 acres, Walmart supercenter, okay? Just the store, not the parking lot. So that's basically the amount of land that's being consumed here to really, do quite an impressive development. And this is not unusual. I would say this is what's now called common best practice, and more wells are being drilled from one small site of 5 acres. It has a lot of efficiency improvements because instead of moving that big drilling rig around all over the horizon, the landscape, you could just keep it in one place and direct the drill bit anywhere you want it to go. It's great. Okay. Yes.
This is a legal question. They're drilling, they're extracting from one site and drilling around. Do they have to buy the rights of the land underneath all those areas, or just not get how that works?
Oh, yes. Oh, yes. Right. So the people that have drilled these wells, it was XTO, needed to go to every single landowner and buy the mineral rights. That can be a big job, especially in an urban area like this. Now, sometimes the mineral rights have been separated from the surface rights, split estate. And there are people at Harvard Law who are actually experts on this. But generally, that's a big part of the sort of gas companies or oil companies' job, is to go around and do exactly that. And so the interesting question is, what happens when that guy doesn't want to sell? So in every state, there is an eminent domain process where if you have a certain percentage of the land for the project, and it doesn't make sense, I mean, you can't avoid his little 3 acres, you can't, I mean, you're going to be draining gas from it whether you want to or not. So that goes to court in an eminent domain process. He is paid fair market value, and he is compelled to give up his mineral rights if the large majority of his neighbors have already done so. So there's some interesting legal implications, and again, your friends at Harvard Law can fill you in on that. Jody Freeman.
Though that depending on from having to buy rights if they don't perf in certain sections of the horizontal?
Well, okay, so the question was, can you avoid buying the rights if you're not actually drilling underneath, but you're only perforating underneath? We actually have a pretty good idea of how far the fractures go. There's a method called microseismic. I've talked about that in previous years, not this year, however. And basically, when you fracture the earth, it's done actually relatively slowly. It takes hours, as you'll see in a minute. Every fracture extension gives off an acoustic emission, like a small earthquake. An acoustic emission, which then can be triangulated with geophones. And so we have a pretty good idea of where the fractures have gone. Nonetheless, we don't really know where the production has come from. So I think there are rules, and I'm not an expert at this, as to who is involved in the unitization, that's the technical term, of this gas field. Certainly everybody in here would be involved. Here, whether this guy is involved, I don't know. That is a legal technicality that I am not up to date on. Yeah. Anybody else have any oil or gas properties they want advice on? Okay, just asking. Okay, now the fracking part, and this is of course the most contentious subject because again, you've all heard about it. It's generated a lot of concern. And I think in some cases rightly so. There are a myriad of issues, but let's just understand the process and to be informed citizens. So just to give you some typical numbers. Typically these horizontal sections that I've just told you how we drill are 5,000 feet long. Now for slick water fracturing, which is sort of kind of the most popular. Doing that fracturing, one well takes 5 million gallons of water, which is 15 acre feet, or to put it in sort of more, to make a fine point of it, 700 to 1,000 truckloads of water. Each well, now I just showed you a project with 19 wells. Each well takes 1,000 truckloads of water. It also takes a lot of sand, typically about a ½ pound per gallon, so you're talking about millions of pounds of sand, each well. And the sand, let me tell you what the sand does, it's important, because once you create the fracture, if you relieve the pressure, which of course you do when the trucks go away, the fractures will close up and basically you haven't done anything. So you put sand in along with the fracture fluid, and then when the fractures try to reclose, the sand sort of prevents them from closing all the way. And this is typical sort of beach sand stuff, like 100 micron sand. And so that's enough to keep it open to get good production. So you're using a lot of sand, a lot of sand. And then chemicals, the industry likes to say, oh, it's only 1% chemicals. Well, 1% of 5 million gallons is 50,000 gallons. That's another 10 trucks. So there's really a lot of inputs. This is a big industrial process. And so again, and here's sort of the picture, and these are water tanks here, and I don't see any sand tanks, but they must be around somewhere. Here's some chemicals. So just in terms of the parameters of the fracturing, the fluid is pumped down at about 4,000 gallons a minute at a pressure of 10,000 psi. That's 24,000 horsepower. Each of these red trucks from Halliburton is good for about 2,000 horsepower. So you think you could get away with 12 of them, but in fact they're only running at 75% efficiency and they keep breaking down. So of course this is Halliburton. So you always have lots of spare trucks. So it really takes 20 trucks to fracture a well, and what's happening here is they're fracturing 2 wells simultaneously. That's what's going on. The process takes to make a fracture takes 1 or 2 hours. It's not something that goes bang. It's sort of like, pumping the brakes, so to speak. It's a hydraulic system. The fracture opens up, sort of in jumps, each one associated with acoustic emission. And So you do that. That takes 1 or 2 hours each. This happens 10 to 40 times per well. So it takes a day or two to fracture a well. You've got, again, a lot of wells on the site. So you might be on the site for a month or two. So for any homeowner nearby, it's going to be a month or two of kind of hell. Then the whole thing goes away. And all you're left with is a pipe coming out of the ground. So that's not so bad. But people in these areas where oil and gas drilling are going on now, what they complain about is the trucks. That's the major sort of on the ground complaint that you hear. Okay, how much is 5 million gallons? Well, 5 million gallons is 5 Olympic-sized swimming pools, each well, 5 million gallons. So that is a lot of water, and of course this has also come into the public debate. Are we using all our water, fracturing wells? So I was asked that question by the California Council of Science and Technology, and so I made this slide really for them. So it's got some California-specific information, but I think it's illustrative. So basically, these days, about 15,000 wells are drilled in the United States for tight oil and gas shale, which involves this massive hydraulic fracturing. So 15,000 wells, each one consuming about 15 acre-feet of water. That's the 5 swimming pools. That's 225,000 acre-feet per year. Now, let's just specialize to California. They aren't doing this yet, but if they did, and you can imagine the largest possible industry in California, that would be about 1,600 wells a year. Again, the 15 acre-feet giving you a California usage of 24,000 acre-feet a year. And compare that to the agricultural use of water in California. 34 million acre-feet of water used to irrigate crops in California. Now, I'm a native Californian. I can tell you California is a very rich state for agriculture. That's a lot of water. If you just look at the water used to irrigate alfalfa, which is basically cattle feed, 5 million acre-feet a year. So comparing that, so that's 20 times more, 200 times more than the amount of water that you would use per annum to do hydraulic fracturing on a very big scale, which is, I would say, maybe even unlikely to see in California, certainly for quite some time. So compared to agriculture, the water use is not huge. So it's good to put it in perspective. So it has local effects, but sort of globally, not so much. Now I'm going to talk a little about the fracture fluids themselves. And again, there's a swirl of environmental controversy about this, which I'm not going to get into, although I'd be happy to if anybody wants to talk about it, perhaps later. But I'm just going to talk about sort of the technology issues connected with hydraulic fracturing fluids. So the two big requirements are, it must be pumpable at high rate without excessive pressure drops. So I've already told you 4,000 gallons a minute. That goes into a 5.5-inch steel bore. So the pressure drop is really, really high. You'll see in a minute how high it is. And if you're not careful, all those trucks basically do nothing for you because you can have enough friction in the 10,000 feet of pipe, 5,000 feet down, 5,000 feet horizontal, that basically you're not putting any pressure on the formation anymore at all, just due to friction of fluid in the pipe, unless you do something special to the fluid, and that's what's called a friction reducer. The other important thing is, I told you that you have to put a lot of sand in, millions of pounds of sand. That has to be transported down the well and into the fracture. So this fluid, whatever it is, whatever you dream up to use, has got to keep proppant in suspension, sand grains in suspension. And if you've ever dumped a pail of sand into a bucket of water, we've all done that as children, you know how fast the water goes straight to how fast the sand goes straight to the bottom. It does not naturally want to stay in suspension. So first, let's look at the friction reducer problem. There are sort of two really popular friction reducers. They're both polymers. They make long chains, and you'll see in a minute why we want long chains. But one is a polymer, the polyacrylamide, which is basically some simple chemical compound. And then there's the more complicated, but much, much cheaper guar. This is an agricultural chemical, sort of used again as cattle feed, but also can make long polymers, long linear polymers. So those are sort of chemistry. These polymers are non-Newtonian, and now we have an expert on that subject in the back, so I can be corrected if I say anything wrong. But basically, what do I mean by non-Newtonian? That means that the viscosity depends on shear rate. So if you have this fluid, this polymer fluid, just standing in a beaker, not going anywhere, it's pretty viscous. And millipascal second equals centipoise. So this is 100 centipoise, that's 1,000 centipoise. So these are typical guar solutions. Again, this is sort of agricultural chemical thing. And at low shear rate or just standing in the bucket, you have viscosities of hundreds of centipoise. But if it has to flow through something, its viscosity is much less. So where it's highly sheared, the viscosity goes down to maybe 10 centipoise or lower. So that's really, really important. And here's kind of a picture taken out of a few books and stuff. Basically, when these polymer solutions are just sitting, quiescent, the polymers tend to ball up and entangle and so on, and you make a viscous solution. But under shear, they tend to stretch out parallel, making a low viscosity flow. And so what happens in a pipe is that a Newtonian fluid like water, oil, whatever, basically has the familiar parabolic profile. I'm sure you've studied this at some point. Parabolic profile, but if you have a shear thinning fluid where the viscosity is high at low shear and low at high shear, basically you get this very non-parabolic shape where the fluid is being sheared, which is near the pipe wall. You get a low viscosity, but in the center, the flow profile tends to flatten out where you have a very high viscosity. So you get this very non-parabolic shape. And the extra little bonus that's sort of thrown in on the way is that if you put a test particle into the pipe in the presence of flow, the particles tend to like to move to the low shear regime in the middle, the high viscous regime in the middle. So all that sand, that proppant, likes to move into the high viscosity place where it's going to be supported. So this is like really magic. This is like magic sauce. It's really great. It does exactly what you want it to do. It's low viscosity with respect to flowing through a pipe. It's high viscosity with respect to suspending proppant. So really great. So of course, this gets more elaborate, and chemists are at work, and they dream up all these really great modifications. So the latest and greatest is what's called cross-link gel, which is those linear molecules that actually have additional linkages to make them more rigid, and that improves the performance in various ways. They're typically used at 20 to 60 pounds per 1,000 gallons, great units. That's like 1/4 to 3/4 of a weight percent. The cross-linkers are various chemicals, whatever. Static viscosity is what I just showed you. Excellent proppant transport. You don't have to pump it quite so fast. You can get away with 50 or 60 barrels per minute, which is like 2,000 gallons per minute, so that's a good thing. These things are expensive, so clients don't like them, but they do a very good job. And just to give you some Reynolds number sort of intuition, the 50 barrels a minute, 4.5-inch pipe, usual density, 1,000 centipoise viscosity gives you a Reynolds number of 1,500, which is just below turbulence, so it's basically kind of laminar, and that's what supports the proppant. And here's a picture of one of these gels taken out of a textbook, and you can see it's pretty gloppy. And let me tell you, when you turn that beaker, the stuff just kind of falls out of it, because in high shear, this becomes very non-viscous, and at the beaker wall, it becomes very easy to flow. So you can okay. The other kind of popular one is called slick water. Much cheaper, so the clients love it, although it doesn't perform as well. But this sort of shows you, and this is sort of much less chemical being used and no cross-linkers, so it's much simpler chemistry. But still, you get this really big reduction in friction. So here's the pump rate on a log scale in barrels per minute. So this is the 4,000 gallons per minute I was referring to. And then the fluid friction also on a log scale in PSI per 1,000 feet. And just brine, which is water, 1 centipoise. Basically, by the time you get to the bottom of a 10,000 foot well, you've got no pressure left to break the rock. But with the slick water, even a small amount of guar actually reduces the friction enough so that it gives you some pressure at the bottom in addition to whatever is lost in the pipe flow. So, like I said, it's kind of magical. But this stuff, because you have only put in a small amount of chemical, its viscosity in quiescent state is only about 3 centipoise, which means that the Reynolds number is about 1,000,000. So here, the proppant is no longer suspended by viscosity. It's actually transported by turbulence in the center of the pipe. So it's a really, from a fluid mechanics standpoint, these two fracture fluids are very, very different. Very, very different mechanism of action. Yes?
Question, or two questions, I guess. How much cheaper is slick water and then is there any understanding of how the long-term performance of a well does between that, given that the slick may not hold the pressures open?
Yes. So the two questions were, how much cheaper is the slick water? And the second question was, does one perform better than the other? And, as far as the cost is concerned, I don't have those kind of dollars per barrel numbers in my head. The slick water is a lot less expensive. You just have a lot less chemicals. The whole thing is simpler, no breakers and so on. But I can't give you a number. As far as performance, it's interesting because in some formations, slick water actually works better in sort of the very brittle formation with low stress anisotropy. A slick water system will give you much more complicated fracturing because it is low viscosity and it will break rock into sort of shatter it into smaller pieces, and that's a good thing. But for a less brittle rock or something with a high stress anisotropy, what you really want is the gel system, because you're going to be, the best solution there is to make one big fracture in which you've transported proppant really well, which is what the gel does. So there are places where sometimes one system is better than the other, and then there's even what's called the hybrid approach, which is you fracture first with slick water to try to make the complex fracture situation, sort of the shatter situation, and then you follow it up with a gel to get some of those paths to be enlarge some of those paths and prop them. So, and that's becoming actually very popular, this hybrid approach of using first the slick water, then the gel. So, some details. Okay, 8 minutes left. Economic and environmental consequences. So this whole business of this gas, shale, and tight oil has been pretty amazing from a resource point of view. So the three biggest hydrocarbon producers in the world are the United States, Russia, and Saudi Arabia. Saudi Arabia has never been a big producer of gas, which are these lighter colors in each bar, with the oil being the darker colors. But way back in 2008, basically Russia and Saudi Arabia were producing much more oil than we were, and Russia was producing substantially more gas. So fast forward to 2013. These are the latest numbers from, again, the Energy Information Administration. These are kind of their latest. Today, we are producing more oil than Saudi Arabia and more gas than Russia. That is amazing. That's remarkable. That hasn't happened in decades. And so I asked myself, well, gee, what about all that gas that's being produced in Qatar and other Middle Eastern nations? We produce today twice as much gas as the entire Middle East. Twice as much gas as the entire Middle East. And there are states now that produce more oil than almost any other nation in the world, except Russia and Saudi Arabia. So It has made a big difference in sort of the energy, we talk about energy security of the United States and balance of trade. When I first gave these lectures 4 years ago, we were spending about $1 billion a day importing oil. Now we're spending $630 million a day. Now that's still a huge number, $630 million a day. But it is 30% less, 35% less than $1 billion a day. So it has made a very big difference in the sort of economic status of the United States. And potentially this could also benefit other nations when they start getting on the bandwagon. Yes?
The Saudis' lack of production of gas, is that because they just flared it?
Yeah. So, oil is so much more valuable than gas, and also it's more transportable for export. The Saudis have ignored gas up till now. So the question is, why haven't the Saudis been producing more gas? Now they want to produce gas because they produce, the 10 million barrels a day. They're burning 1 or 2 million barrels a day for themselves, for their air conditioning and their desalination of water, plus growing the alfalfa. So they're realizing that they need a cheaper domestic source of gas. Qatar will not sell it to them because Qatar gets more money selling to Japan, friendly air neighbor. So they are actively prospecting for shale gas. Yes. Okay. So this is, again, from the U.S. Energy Information Administration. This is kind of the overall oil picture. We're sort of consuming sort of 18 to 20 million barrels a day of oil. The conventional crude oil production has been sort of declining steadily since 1970 when it peaked out at 9.6 million barrels. And we thought we were going to be on that trend forever, but this tight oil that I've just been telling you about is now a huge big bump. This natural gas plant liquids, I haven't really gone into that, but that is another byproduct of tight oil production, so there's a huge bump of that. And then that means that our imports are going to be which is the purple stuff, is going to be very much smaller. So looking at these numbers a little bit more closely, these are the very latest numbers out of EIA just a few weeks ago. This is their crude oil production. The reference case is what I just showed you, sort of hitting a historic high, which occurred in 1970. We're going to hit that again before 2020. But then they've got very big error bars on that. These are basically the error bars. And what I told Administrator Szyminski when he was here a few weeks ago was that I don't believe any of these numbers. It's just because the technology uncertainties are so huge. I mean, these are unconventional. We know we have not optimized our production technology. We don't know where it's going to go. So these are very uncertain. And let me just give you in the last few minutes my reasoning for why it's so uncertain. Because we've been producing conventional oil for 150 years, we've got lots and lots of ways to get it out of the ground. Primary recovery, secondary recovery, tertiary recovery. I'm not going to talk about every box. But we've got lots and lots of things in the toolbox to use, and that's why we're able to get 50% of the oil in a reservoir out of the ground from conventional reservoirs. 50% doesn't sound very good, but it is the result of 150 years of development. It used to be much worse. Here is the story with tight oil. Lots of white space. All these other methods that we have just spent 150 years working on don't work. They don't work. Because remember, the conventional reservoir is buoyancy driven, the unconventional is not, and that takes away a lot of tricks that we'd otherwise use. So today, we're getting about 5% of the oil out of the ground from these tight oil reservoirs, which is pathetic. 5%, not 50% like we're used to, 5%. And we have no idea if we can get any more, and if so, how to do it. So there are vast uncertainties in where we go from here. Gas situation, I'm it's 359, I'm not going to dwell on this. Basically, like the oil, we're now producing a lot more gas. We used to thought we'd have to import a lot of gas from Canada and by liquefied natural gas. Now we're going to be exporting gas.
Why are we importing and exporting to Canada?
Yeah, it's sort of a energy arbitrage. Basically, Chicago uses a lot of gas, and the closest gas field might be in Canada. But on the other hand, Mexico needs gas from us, and our big gas field is in Texas. So yeah, it's where the pipelines are running and where it's cheapest to send it on a transportation cost basis. Yeah, that's a good question.
John, I mentioned Boston is at the end of the pipeline, so we import LNG. And
Yeah.
likely always will until someone builds another pipeline.
And as Energy Secretary Moniz just pointed out the other day, Boston does not have enough pipelines. We absolutely need to have more gas coming into this area, especially if we shut down our nuclear plant at Vermont Yankee and so on. You know, it's 4 o'clock. I have some really fascinating slides left here about, so you could come up to me afterwards and I'll go through this if you wish. But basically, the argument here that I'm going to make is that, in the last 30 seconds, is that although people thought that it was a great idea to substitute gas for coal in electric power production, that turns out really not to be true when you look at all the numbers on a life cycle basis. Natural gas really has no advantage over coal from a greenhouse gas perspective. Now, it does have an advantage in that there's a lot less other ancillary problems like acid rain and arsenic and all that other stuff, dying miners. But if you look through the analysis carefully, and I'll be happy to review this with anyone who wishes to see it, basically natural gas has no advantage over coal in as far as greenhouse gas output from power gen. And it's an example, I mean, in a way it's a little discouraging, but I think we as sort of educated people and technical people shouldn't be discouraged, but should be looking at these facts really carefully and figuring out how to do it better. So that's kind of the take-home message. Anyway, that sort of concludes the hour. This is the old-fashioned way, primary recovery of oil. And I'll certainly be happy to stay as long as you like and answer questions. Thank you.